So we're going to do number 9 from lesson 1.4. It's on page 40. The problem reads, Liz works at a ballpark selling bottled water. She sells 37 bottles in one shift. Okay? The large bottles sell for $5 each, and the small bottles sell for $3 each. At the end of one game, she has taken in $131. So whenever I do a problem, I try to read through it twice. The first time to understand what it's going to ask me. The second time to set up all my variables. So again, Liz works at a ballpark selling bottles. She sells 37 in one shift. So I know that something's probably going to equal 37. If maybe she only sells one type of bottles, maybe she sells two. Next sentence says the large bottles sell for 5 and the small bottles sell for 3. So I know she's selling large bottles and small bottles. So that's where I can set up my let statement. I'm going to say let L equal large bottles. Let S equal small bottles. Okay? And I know if I add all of the large bottles she sold with all of the small bottles she sold, it will equal 37 because she sold 37 in one shift. So that will be my first equation. My first equation is all of the large bottles plus all of the small bottles are going to equal 37. Equation 2 says the large bottles sell for $5 each, small for 3, and at the end of one game she has taken in $131. So again, she has taken in $131, so something's going to equal 131. Large bottles sell at $5 each, so that's 5 times each large bottle she sells. And small bottles sell for $3 each, so that's 3 times all of the small bottles she sells. If we multiply 5 by the number of large bottles and 3 by the number of small bottles, we're going to end up with $131. So what I've done is I've set up 2 linear equations to find the point of intersection, which will tell us how many large and how many small bottles she sold. So we have our 2 equations. Now that we have those, I can use either, there are 3 types of solving. See if you guys remember them. What's the first way to solve something that we learned? Something before that. Graphing. I could graph both of these linear systems, maybe call L my y and S my x, and find the point of intersection by where the 2 lines cross. What's the second way we learned? I can substitute. Substitute one variable in for the other and back. Or finally, what did we learn yesterday? So these are the 3 different methods we know to solve linear systems. Since yesterday's work was elimination, I'm going to use elimination to solve these. So when I look at them, remember, in order to solve for elimination, I need the coefficients in front of the variables to be the same. So which variable would you guys like to eliminate? S? Okay, we're going to eliminate S. Now, one of the coefficients is a 3. Thank you, Ryan. The other one is a 1. What will I have to do to make one of the equations, or both the equations, have the same coefficient? An A. Okay, so if I multiply the first equation, the entire thing by 3, or did you say negative or positive? Sure. We could do negative 3. Our coefficients, the absolute value of them, will both be 3. So let's try that. Equation 1, we have L plus S equals 37. Okay. I'm going to multiply every term, that's a negative, sorry, by negative 3. Our new equation will be negative 3L minus 3S equals negative 101. Okay? Then I'm going to bring down equation 2, which is 5L plus 3S equals 131. So now that my coefficients are the same, I can eliminate. What operation do I need to apply when combining these equations to eliminate, Mark?
It's negative 111.
Is it 111? Thank you. 21, 2, 9. Yeah, that is 11. Good. What operation do I need to use in order to eliminate one of the variables? So I have a coefficient of -3 and +3. How can I combine those two to eliminate each other? I'm trying to create a 0. I need to add them together. Okay? Because one's negative and one's positive. If I add the equations together, -3 plus +3 will eliminate each other. So let's get rid of the first one. -3 and +3 is 0s. 0s is just 0, so I don't need to write it in. What about my L's? -3 plus 5. 2L. How about our other one? -111 plus +131. 20. So, I've got 20. Let's just put these together. 2L is equal to 20. What do I need to do next? Divide by 2. L is equal to... So what have we just figured out?
She sold 10 large bottles.
Okay, we know she has now sold 10 large bottles. So I can call it my... Maybe our L and our S. Kind of like a point of intersection. L is 10. Now, I can either eliminate again to solve for S, or I can substitute in. Which would you guys like to do? Okay, let's substitute in. So now that we have L, I'm going to use equation 1 because it's actually probably the easiest to work with. We know that L... Thank you, guys. We know that L is 10. So I'm going to replace the L in equation 1 with the number 10 plus S equals 37. I need to set the equation equal to S, so I'm going to move 10 to the other side, which will become negative on the other side. So S is equal to 37, subtract 10. S is equal to 27. So how many small bottles did she sell? 27. So 10 large and 27 small bottles is what she sold in her shift. So I could have multiplied this equation by +3, and then I would have had +3L and +3S. The only difference would have been I would have had to subtract the equations. Okay? But if you choose to multiply by a negative, that's fine as long as the coefficient's absolute value is the same. So as long as the 3's are both 3. If we have a negative and a positive, that's fine. We just got to figure out which operation we're going to use to eliminate them. So you could either multiply by positive or a negative. Just make sure you know which operation will get rid of the variable. Okay, so we're going to solve the same question, but this time we're going to use graphing to solve this question. So I have my two equations, 1 and 2. Now, in order to graph, we're used to having an x and a y-axis. So if you notice I put a little s and an L, I'll get rid of those. We're used to having a y and an x. All we have to do is choose which variable we want to measure on which axis. So I'm going to say that my y will be S, my small drinks, and my x will be my L, my large drinks. Okay? And remember, to graph, we set things equal to y equals mx plus b. So, since we're using the letter S to represent our y, we're going to be setting each of the equations equal to S. So I'm going to rearrange these two equations. So equation 1, we had L plus S equals 37. S is going to be our y, and L is going to be our x. So I'm going to rearrange this so it's set equal to S. I move the L to the other side. I end up with S is equal to 37 minus L. Okay? I'm going to show you y equals mx plus b. We said our S will be our y, and we had 37 minus L. We're going to rearrange that because L is our x. We said that our x-axis will be measured with large drinks. So I'm just going to rearrange this so it says S is equal to negative L plus 37. Once I've done that, my slope is the number in front of the L. Okay? So the number in front is just a negative. In other words, it's negative 1. So our slope is negative 1. We'll put it over 1. And our y-intercept is going to be whatever constant number we have. So our y-intercept will be 37. Okay? We're also going to rearrange our other equation, which was 5L plus 3S equals 131. So equation 2. 5L plus 3S equals 131. Remember we said our S is what our Y is going to be. So I'm going to set the equation equal to S. So I need to move 5L to the other side of the equation. So we'll get 3S is equal to 131 minus 5L. And actually, I still need to set it equal to just S, so I'm going to have to divide each term by 3. When I do that, I end up with S is equal to 47 minus 5 over 3L. So again, let's look at our y equals mx plus b. I'm going to rearrange that equation to have our L in front, so 5 over 3L plus 47. Our slope for our other one is negative 5 over 3. And our y-intercept is positive 47. So now that I have a slope and an intercept for both of those, I'm going to graph the two. So when we looked on our graph, we discovered that for our first variable, we had b is 37 and our slope is negative 1. So I got to find 37 on this graph, which is going to be roughly here. Okay? And what happens with graphing, and this is why substitution and elimination are more accurate, is that it becomes hard to estimate where the line's going to go. I know that one of the points will be at 20 and 20. Oh, no, sorry. Yeah. One point will be 20 and 20. So I'm going to graph my line. Here's the slope of one of my lines. The other line, our y-intercept, is positive 47, so it's roughly here. And it has a slope of negative 5 and 3. So it actually has an, what is it, x-intercept? So we graph our other line by slope. And if you noticed, our graph right now, it's actually very hard to tell where these two lines meet. Okay?
Right there.
It's right there, but what are these numbers? It's pretty hard to tell. We know by our elimination before, we knew that our numbers were going to be L was 10 and S was 27. But because our graph was not large in scale enough to be accurate, it can be very tell. Those could be 9, it could be 29. I'm not 100% sure. That's why using substitution and elimination is usually a more accurate way of solving linear systems. Okay? Jake, does that help for